In 1957, a young physicist named Hugh Everett III submitted his PhD thesis at Princeton University. It was just 137 pages long. Its title was On the Foundations of Quantum Mechanics. Inside, he proposed something that seemed to border on madness. The established view of quantum physics, known as the Copenhagen interpretation, said that a particle like an electron exists in a haze of possibilities until it's measured. When measured, this cloud of potential outcomes collapses into one single reality. We see the electron here and not there. Everett's idea was radically different. He suggested the collapse never happens. Instead, at the moment of measurement, reality itself splits. The universe branches into multiple copies. In one universe, the electron is here. In another, completely separate universe, it's there. Every quantum event happening constantly everywhere creates a cascade of new universes. His thesis advisor, the famous physicist John Wheeler, was cautiously supportive, but worried. He took Everett to Copenhagen to present his idea to Niels Bohr, the patriarch of quantum mechanics. The meeting was a disaster. Bohr and his colleagues dismissed the theory completely. They saw it as unnecessarily extravagant. Why invent an infinite number of unseeable worlds just to solve a mathematical quirk? Everett was crushed. He left academia soon after. He went to work for the Pentagon, applying his mathematical skills to Cold War military strategy. He rarely spoke of his theory again. For years, the many worlds idea was a footnote, a weird little curiosity. But the idea didn't die. It was too powerful. It offered a way out of the paradoxes of quantum mechanics. Decades later, physicists like Bryce DeWitt revived and championed Everett's work, giving it the name the many worlds interpretation. Today, it's a leading contender for how reality actually works. It suggests that somewhere, in another branch of reality, a version of you is living out the consequences of a different choice. A version of you who took that other job, a version of you who never met your partner. An infinite number of yous spun off from an infinite number of quantum decisions, each convinced they are the only one. Hugh Everett III's lonely, rejected idea from 1957 didn't just change physics. It completely shattered the notion of a single, unique existence, leaving us to wonder which of our infinite stories is the one we happen to be in. Number 21, The Ghost in the Machine will finally get a name. Vera Rubin noticed something strange in the 1970s. She was studying the Andromeda Galaxy. She saw that the stars on the outer edges were moving just as fast as the stars near the center. This made no sense. According to Newton's laws, they should have been moving much slower. The only way to explain their speed was if there was a huge amount of invisible matter surrounding the galaxy, a massive halo of stuff we couldn't see. Her work was initially met with a lot of skepticism, but the evidence kept building. Today, we know that about 85% of all the matter in the universe is this invisible stuff. We call it dark matter. Fritz Zwicky had actually proposed the idea of Dunkel Materie back in 1933 while observing the Coma cluster of galaxies, but his work was largely ignored for 4 decades. We know it's there. We can see its gravitational effects everywhere. It bends light from distant galaxies. It holds our own Milky Way together. Without it, our galaxy would fly apart. But we still have no idea what it is. The leading candidate for decades was a hypothetical particle called a WIMP. That stands for Weakly Interacting Massive Particle. WIMPs would be heavy, slow-moving particles that don't interact with light or normal matter, except through gravity and the weak nuclear force. The idea was compelling. It fit neatly into theories like supersymmetry, so we built experiments to find them. These experiments are usually built deep underground in places like the Sanford Underground Research Facility in South Dakota or the Gran Sasso National Laboratory in Italy. They go deep to shield the sensitive detectors from cosmic rays and other radiation that could create false signals. The concept is simple. You take a huge vat of a pure substance like liquid xenon or argon, and you wait. You wait for a WIMP from the halo of dark matter surrounding our galaxy to fly through the Earth and by pure chance hit one of the nuclei in your detector. This collision would produce a tiny flash of light or a small electrical charge which ultrasensitive sensors would then pick up. We've been running these experiments like Aluak Zeppelin and X-Naught for years. We've made them bigger and more sensitive. And so far we have found nothing, absolutely nothing. The null results have caused a crisis in the particle physics community. Many are starting to think we've been looking for the wrong thing. Maybe dark matter isn't a WIMP. So the focus is shifting to other candidates. One of the most popular alternatives is the axion. Axions are incredibly light, hypothetical particles proposed in the 1970s to solve a different problem in particle physics. If they exist, they would have been produced in huge numbers in the early universe and would now form a vast, cold cloud of dark matter. And experiments like the Axion Dark Matter e-experiment ADMX are looking for them. Instead of a vat of liquid, ADMX uses a powerful magnetic field inside a resonant cavity. If an axion passes through the magnetic field, it should, in theory, convert into a microwave photon, a tiny blip of light that the experiment can detect. The search is painstaking. It's like tuning a radio, slowly sweeping through frequencies to find a very faint station. There are other more exotic ideas too. Maybe dark matter is made of sterile neutrinos, heavier cousins of the familiar neutrinos we know. Maybe it's made of primordial black holes, tiny black holes that formed in the first second of the universe's existence. Or maybe dark matter isn't a single particle at all. Maybe there's a whole, dark sector of particles with their own forces interacting with each other, but almost totally ignoring our world of normal matter. The next big discovery could be the first confirmed detection from one of these experiments. It might be a clear signal from a xenon detector deep underground. It might be a faint microwave hum from an axion detector. Or it might be an unexpected anomaly at the Large Hadron Collider where missing energy in a particle collision points to the creation of a new invisible particle. Finding this particle would be one of the biggest discoveries in the history of science. It would finally give a name to the ghost in the cosmic machine, the invisible substance that sculpts the universe on its grandest scales. Number 20, we will understand why the universe is expanding faster and faster. In 1998, two separate teams of astronomers were doing what they thought was a routine job. They were using powerful telescopes to look at distant type Ia supernovae. These exploding stars are incredibly useful because they all have roughly the same intrinsic brightness. They are standard candles. By measuring how faint they appear from Earth, you can calculate how far away they are. By measuring their redshift, you can calculate how fast they are moving away from us. The goal was to measure how much the expansion of the universe was slowing down. Everyone knew gravity was pulling everything together, so the expansion had to be decelerating. It was just a matter of measuring by how much. Both teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Ries, found the exact opposite. The distant supernovae were fainter than they should have been. This meant they were farther away than expected. The only way for that to be true was if the expansion of the universe wasn't slowing down. It was speeding up. The discovery was shocking. It was like throwing a ball into the air and, watching it accelerate upwards into the sky instead of falling back down. It won the three team leaders the Nobel Prize in Physics in 2011, but it left cosmology with its biggest mystery. Something is pushing the universe apart, counteracting gravity on the largest scales. We call this something dark energy. The name is really just a placeholder for our ignorance. We know it makes up about 68% of the energy density of the universe. Dark matter makes up 27%. Normal matter, the stuff that makes up stars, planets, and us, is less than 5%. We live in a universe dominated by two things we cannot see and do not understand. The simplest explanation for dark energy is something Albert Einstein proposed and then discarded. In 1917, he added a term to his equations of general relativity to make the universe static, which was the prevailing belief at the time. He called it the cosmological constant. When Edwin Hubble discovered the universe was expanding, Einstein called the cosmological constant his biggest blunder. But it turns out he may have been right for the wrong reasons. The cosmological constant, represented by the Greek letter lambda, can be interpreted as the energy of empty space itself, the energy of the vacuum. According to quantum field theory, the vacuum is not empty, it's fizzing with virtual particles constantly popping in and out of existence. This activity should give space its own intrinsic energy. This vacuum energy would have a constant density everywhere and would create a kind of negative pressure pushing space apart. The problem is, when we try to calculate how much vacuum energy there should be, the number we get is absurd. It's about 10 to the power of 120 times larger than what we observe. This is the worst prediction in the history of physics. It's called the cosmological constant problem. Because the cosmological constant idea has this massive problem, people have looked for alternatives. One idea is called quintessence. Unlike the cosmological constant, which is a constant energy density, quintessence is a dynamic field that can change over time and space. Think of it as a fifth fundamental force of nature, one that has only become dominant in the last few billion years of cosmic history. If dark energy is quintessence, its strength might not be constant. It might be getting stronger or weaker. This would have profound implications for the future of the universe. If it gets stronger, it could lead to a big rip where the expansion becomes so violent it tears apart galaxies, stars, and even atoms. The next big discovery will be to figure out which of these ideas, if any, is right. So telescopes like the Euclid Space Telescope and the Vera C. Rubin Observatory are designed to do just that. They will create vast 3D maps of the universe, measuring the positions and distances of billions of galaxies with unprecedented precision. By studying how the distribution of galaxies has changed over cosmic time, they can measure the history of the universe's expansion in detail. They will be looking for any deviation from the constant energy density predicted by the cosmological constant model. If they find that the strength of dark energy has changed over time, it would rule out the cosmological constant and point towards a dynamic field like quintessence. This would open up a whole new realm of physics. It would mean that the vacuum of space isn't just a static stage for the cosmos, but an active player whose nature we are only just beginning to grasp. Number 19, the first second of the universe, will no longer be a mystery. The theory of cosmic inflation was proposed in the early 1980s by physicists Alan Guth and André Linde. It addresses some major puzzles in the standard Big Bang model. For example, why is the universe so remarkably uniform on large scales? The cosmic microwave background radiation, the leftover heat from the Big Bang, has almost the same temperature everywhere we look, to 1 part in 100,000. This is strange because regions of the sky that are on opposite horizons were never in causal contact with each other in the standard model. They couldn't have exchanged heat to even out their temperatures. Inflation solves this by proposing a period of hyper-accelerated expansion in the first fraction of a second after the Big Bang. Between about 10 to the minus 36 and 10 to the minus 32 seconds, the universe expanded by a factor of at least 10 to the 26. A region of space smaller than a proton balloon to the size of a grapefruit. This expansion happened much faster than the speed of light. That doesn't violate relativity because it was space itself that was expanding, not objects moving through space. This rapid stretching would have smoothed out any initial wrinkles or irregularities, explaining the universe's uniformity. Inflation also explains why the universe appears to be geometrically flat. According to general relativity, spacetime can have 3 possible geometries: closed, like a sphere, open like a saddle, or flat like a sheet of paper. Our measurements show the universe is extremely close to flat. This is a very special condition. If the early universe had been even slightly curved, that curvature would have been magnified over 13.8 billion years. Inflation explains this by stretching the universe so much that any initial curvature would be stretched out to near perfect flatness, just like how the surface of the Earth seems flat to us even though it's a sphere. Inflation also provides the seeds for all the structure we see today. Tiny quantum fluctuations in the energy field driving inflation would have been stretched to astronomical scales. These tiny density variations became the seeds around which galaxies and clusters of galaxies later formed. The theory is beautiful and elegant, and it solves many problems, but is it right? We need direct evidence. The smoking gun for inflation would be the detection of primordial gravitational waves. So these are ripples in the fabric of space-time that would have been generated by the violent accelerated expansion of inflation. These gravitational waves would be imprinted on the cosmic microwave background CMB radiation. They would leave a faint but specific swirling pattern in the polarization of the CMB light. This pattern is called B-mode polarization. Finding this specific B-mode signal is the holy grail for cosmologists studying the early universe. In 2014, a team working on the BICEP 2 experiment at the South Pole announced they had detected this signal. The news caused a massive stir in the physics world. It seemed like the evidence for inflation had finally been found. But the excitement was premature. Further analysis by the Planck satellite team showed that the signal BICEP 2 had seen was most likely caused by interstellar dust in our own galaxy, which can also polarize light and mimic the B-mode signal. It was a major disappointment. The search continues. A new generation of experiments like the Simons Observatory and CMB-S4 are being built in the Atacama Desert in Chile and at the South Pole. These experiments will have thousands more detectors than their predecessors, and will be able to observe the CMB in many more frequencies of light. This will allow them to carefully subtract the foreground contamination from dust, and hopefully isolate the faint primordial B-mode signal. If they find it, it will be a monumental discovery. It would be direct evidence of a time when the universe was less than a trillionth of a second old. It would confirm the theory of inflation and give us a window into physics at energies far beyond what we can ever hope to achieve in particle accelerators on Earth. It would be our first direct glimpse of the moment of creation. Number 18, we will witness the birth of the first stars. For about 400,000 years after the Big Bang, the universe was a hot, dense soup of protons, electrons, and photons. Light was trapped, constantly scattering off free electrons. Then the universe cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This event is called recombination. Suddenly, light was free to travel through space. This is the light we see today as the cosmic microwave background. After this, the universe entered a period known as the Cosmic Dark Ages. There were no stars, no galaxies, just vast clouds of neutral hydrogen and helium gas in the growing darkness. This period lasted for a few 100 million years. Then, gravity began to pull the densest regions of gas together. The gas clouds collapsed, heated up, and eventually the first stars ignited. Their light ended the Dark Ages and began the process of reionization, where their intense ultraviolet radiation stripped the electrons off the neutral hydrogen atoms again, making the universe transparent as it is today. These first stars, which astronomers call population the third stars, would have been very different from the stars we see today. They were forged from the pure hydrogen and helium created in the Big Bang. They contained no heavy elements, what astronomers call metals, because they lacked these heavier elements which are efficient at radiating away heat. The gas clouds they formed from couldn't cool as effectively. This meant they had to become much more massive before they could collapse and ignite nuclear fusion. Models predict that these population, the third stars, were giants, hundreds of times more massive than our sun. They would have been incredibly hot, incredibly bright, and would have lived for only a few million years before exploding as spectacular supernovae. These explosions seeded the universe with the first heavy elements, paving the way for the next generation of stars, population the second, and eventually our own sun, a population Y star, which are rich in these metals. We have never directly seen a population, the third star. They are incredibly far away and lived a very long time ago. Looking for them means looking back in time to the edge of the observable universe. This is one of the primary missions of the James Webb Space Telescope, JUICed, with its huge mirror and its sensitivity to infrared light. JUICed is designed to capture the faint red-shifted light from the very first galaxies. The expansion of the universe stretches the light from these distant objects, shifting their bright ultraviolet light into the infrared part of the spectrum where JUICed excels. Already, JUICed has found galaxies that existed just 300 million years after the Big Bang, much earlier than we thought possible. These galaxies are small and clumpy, and they likely contain some of the first stars. The next big discovery will be the direct detection of light from a population, the third star, or a cluster of them. This might not come as a direct image of a single star, which would be too faint even for JUICed. It's more likely to come from finding a very early galaxy whose light spectrum shows the unique chemical signature of population, the third star's pure hydrogen and helium, with a complete absence of heavier elements. Another possibility is to find the remnants of one of these stars after it exploded. Some theories predict that these massive stars would have exploded in a way called a pair instability supernova, a uniquely powerful type of explosion. If we could detect the light from one of these events, it would be a direct confirmation of our models of the first stars. Finding these first beacons of light would be like finding the first chapter of the cosmic story. It would fill in a huge gap in our understanding of how the universe went from a simple, dark place to the complex, light-filled cosmos we see today. Number 17, the cosmic speed limit discrepancy will be resolved. Edwin Hubble discovered in the 1920s that the universe is expanding. He found that the farther away a galaxy is, the faster it is moving away from us. The rate of this expansion is called the Hubble constant, or H0. Measuring the exact value of this constant has been a major goal of cosmology for a century. It tells us the age of the universe, its size, and its ultimate fate. The problem is, we have two extremely precise ways of measuring it, and they give two different answers. This disagreement is known as the Hubble tension, and it's one of the biggest problems in modern cosmology. The first method measures the expansion rate in the late or local universe. It uses a technique called the cosmic distance ladder. Astronomers start by measuring the distance to nearby stars called Cepheid variables. These stars pulsate at a rate that is directly related to their intrinsic brightness. By measuring their pulsation period, we know how bright they really are, and by comparing that to how bright they appear, we can calculate their distance. Once we have the distance to nearby galaxies containing Cepheids, we can use those galaxies to calibrate the brightness of Type Ia supernovae. These supernovae are the standard candles we use to measure distances to even more remote galaxies. This method, led by Adam Ries and the SH0ES supernova H0 for the equation of state of dark energy team, gives a value for the Hubble constant of about 73 kilometers per second per megaparsec. This means that for every 3.26 million light years a galaxy is away from us, it appears to be receding about 73 kilometers per second faster. The second method measures the expansion rate in the early universe. It uses the cosmic microwave background CMB, the faint afterglow of the Big Bang. Satellites like the Planck Observatory have mapped the CMB in incredible detail. The CMB is not perfectly uniform. It has tiny temperature fluctuations. These fluctuations correspond to slight density variations in the early universe. By analyzing the size and distribution of these spots, cosmologists can use our standard model of cosmology, called the lambda CDM model, to predict what the expansion rate should be today. This method consistently gives a value for the Hubble constant of about 67 kilometers per second per megaparsec. The two measurements are incredibly precise. The error bars on each measurement do not overlap. The chance that this difference is just a statistical fluke is less than 1 in a million. So we have a real problem. One or both of our measurement techniques are wrong, or our standard model of cosmology is incomplete. Maybe there is some unknown systematic error in the distance ladder. Perhaps our understanding of Cepheid, variable stars, or supernovae is flawed. Or maybe the error is in the early universe measurement. Perhaps our interpretation of the CMB data is missing something. Many physicists, however, believe the tension is pointing to new physics. It could be a sign that something is missing from the lambda CDM model. One idea is a new form of early dark energy that was active in the first few 100,000 years after the Big Bang, which would have changed the expansion rate of the early universe in a way that could resolve the discrepancy. Another possibility is a new type of neutrino, a sterile neutrino, or some unknown interaction between dark matter and radiation. The next big discovery will be the resolution of this tension. The Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope will measure supernovae and galaxy distributions with much greater precision, potentially finding flaws in the local measurement. At the same time, new CMB experiments like the Simons Observatory will refine the early universe measurement. Another avenue is gravitational waves. When two neutron stars merge, they emit both gravitational waves and light. The gravitational waves give us a direct measure of the distance to the merger, and the light gives us its redshift. These standard sirens provide a completely independent way to measure the Hubble constant. So far, we have only a few such events, but as the LIGO-Virgo-Cagra network of detectors becomes more sensitive, we will have many more. Finding out why our two best measurements of the universe's expansion rate disagree will either solidify our current understanding of the cosmos, or more excitingly, force us to rewrite it. Number 16 black holes will be forced to reveal their secrets. In the 1970s, Stephen Hawking made a startling discovery. He combined the laws of general relativity with quantum mechanics and found that black holes are not completely black. They should slowly radiate away their mass through a process now known as Hawking radiation. This radiation is caused by quantum effects near the event horizon, the point of no return. According to quantum mechanics, pairs of virtual particles and antiparticles are constantly popping into and out of existence in empty space. Usually, they annihilate each other almost instantly, but if a pair is created right at the edge of a black hole's event horizon, one particle might fall in while the other escapes. The escaping particle becomes real and carries away a tiny amount of the black hole's energy. To an outside observer, it looks like the black hole is glowing very, very faintly. Over immense timescales, a black hole would radiate away its entire mass and evaporate completely. This leads to a profound paradox known as the black hole information paradox. One of the fundamental principles of quantum mechanics is that information can never be destroyed. The information about the initial state of a system is always preserved, even if it gets scrambled. For example, if you burn a book, the information in the book isn't truly gone. In principle, if you could collect every particle of smoke and ash and measure their exact states, you could reconstruct the original book. But what happens if you throw the book into a black hole? The information about the book seems to fall past the event horizon and is lost to the outside world. Then, the black hole slowly evaporates, emitting only random thermal Hawking radiation. This radiation seems to be completely featureless. It doesn't seem to contain any information about what fell into the black hole. When the black hole is completely gone, the information about the book seems to be gone with it forever. This violates the laws of quantum mechanics. This paradox puts our two most fundamental theories of the universe, general relativity and quantum mechanics, in direct conflict. General relativity describes the smooth, continuous space-time of a black hole's interior, though quantum mechanics demands that information is preserved. For decades, physicists have been trying to solve this puzzle. There are many proposed solutions. One idea proposed by Gerard 't Hooft and Leonard Susskind is the holographic principle. This suggests that all the information about what falls into a black hole isn't actually inside it. Instead, it's encoded on the two-dimensional surface of the event horizon like a hologram. When the black hole evaporates, this information is somehow imprinted on the outgoing Hawking radiation. Another more radical idea is the firewall paradox, proposed by Joseph Polchinski and others in 2012. It suggests that the event horizon is not an empty, drama-free place as general relativity predicts. Instead, it's a firewall, a high-energy region that would incinerate anything that tries to cross it. This would solve the information paradox because the information never actually makes it inside the black hole. But it would violate Einstein's equivalence principle, a cornerstone of general relativity, which states that a freely falling observer should feel no gravity and notice nothing special as they cross the event horizon. The next big discovery will likely come from a theoretical breakthrough that reconciles these ideas, perhaps as part of a complete theory of quantum gravity. But there might be an observational component too. The Event Horizon Telescope, which gave us our first images of black holes, could potentially probe the regions near the event horizon with enough precision to look for deviations from general relativity. Gravitational wave observatories like LIGO might be able to detect subtle echoes in the signal from merging black holes, which could hint at new physics at the event horizon. Resolving the information paradox is more than just an academic puzzle about black holes. It's about finding the fundamental rules that govern reality at its deepest level. The solution will likely force us to completely rethink our concepts of space-time, information, and reality itself. Number 15, we will find evidence for extra dimensions. The world we experience has 3 dimensions of space length, width, and height, and 1 of time. But for over a century, some physicists have suspected that there might be more. The idea first came from Theodore Kaluza in 1921. He showed that if you wrote out Einstein's equations of general relativity in 5 dimensions, 4 of space, 1 of time, you could derive not only general relativity, but also Maxwell's equations for electromagnetism. It seemed like a miracle. The 5th dimension could unify gravity and light. But where was this extra dimension? A few years later, Oscar Klein suggested that it was curled up into a tiny circle so small that we can't see it. Imagine a garden hose. From far away, it looks like a one-dimensional line, but if you get very close, you see it has a second, circular dimension. The idea is that at every point in our familiar 3D space, there is a tiny, curled-up extra dimension. This idea was largely forgotten for decades, but it was revived in the 1980s with the development of string theory. String theory is an attempt to create a theory of everything that unifies all the fundamental forces of nature, including gravity. In string theory, the fundamental constituents of the universe are not point-like particles, but tiny, vibrating, one-dimensional strings. Different vibrations of these strings correspond to different particles. For the mathematics of string theory to work, it requires the existence of extra spatial dimensions. The most popular versions of the theory require a total of 10 dimensions, 9 of space, and 1 of time. That means there are 6 extra spatial dimensions curled up at every point in space. These dimensions are thought to be compacted into complex shapes known as Calabi-Yau manifolds. For a long time, these extra dimensions were thought to be curled up at the Planck length, an incredibly tiny scale of about 10 to the minus 35 meters, far too small to ever be probed by experiments. But in the late 1990s, physicists Nima Arkani Hamed, Savas Dimopoulos, and Gia Diwali proposed a new idea called the large extra dimensions model. They suggested that some of these extra dimensions could be much larger, perhaps as large as a millimeter. We wouldn't notice them because the particles and forces of the standard model, like electromagnetism and the nuclear forces, are confined to our 3D brain, like beads on a wire. But gravity is different. In string theory, gravity is caused by the closed loops of strings' gravitons, which are not stuck to the brain and can travel freely through all the extra dimensions, the bulk. This could explain why gravity is so much weaker than the other forces. It's because its force is leaking out into the extra dimensions. This idea is testable. If there are large extra dimensions, we might be able to create tiny microscopic black holes at the Large Hadron Collider LHC. If gravity gets much stronger at very small distances because it's no longer diluted by the extra dimensions, then smashing protons together at high energies could create these mini black holes. They would be harmless, evaporating almost instantly via Hawking radiation into a spray of other particles. Finding such an event at the LHC would be a stunning confirmation of extra dimensions. So far, we haven't seen any. Another way to search for them is through high-precision tests of gravity. If there are extra dimensions, Newton's inverse square law of gravity should break down at very short distances. Experiments are being conducted that measure the force of gravity between two objects at sub-millimeter scales, looking for any deviation. So far, Newton's law holds up. The next big discovery could be the first hint of evidence for these hidden worlds. It might be a strange signal at the LHC or a tiny anomaly in a gravity experiment. It would mean our universe is vastly larger and more complex than we ever imagined. Number 14, a unified theory of everything will start to take shape. Physics today is based on two incredibly successful theories, general relativity and the standard model of particle physics. General relativity describes gravity and the universe on large scales, stars, galaxies, the expansion of the cosmos. The standard model describes the other three fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, and all the known elementary particles. Both theories work perfectly in their own domains, but they are fundamentally incompatible. General relativity is a classical theory that describes a smooth, deterministic spacetime. The standard model is a quantum field theory that describes a fuzzy, probabilistic world. Trying to combine them leads to mathematical nonsense. The equations break down and give infinite answers. This is a huge problem because there are places in the universe where both theories must apply, like in the center of a black hole or at the moment of the Big Bang. We need a theory of quantum gravity to describe these extreme environments. Finding this theory, a theory of everything that unites all four forces, is the ultimate goal of fundamental physics. There are two main contenders for a theory of quantum gravity. The most famous is string theory. As we've discussed, string theory replaces point-like particles with tiny vibrating strings and requires extra spatial dimensions. It has the major advantage of naturally incorporating a particle that behaves just like the graviton, the hypothetical quantum particle of gravity. It also provides a framework for unifying all the forces and particles into a single, elegant structure. The problem with string theory is that it is incredibly difficult to test. The strings themselves are too small to ever be seen directly. And the theory doesn't make just one prediction. It gives a landscape of about 10 to the 500 possible universes, each with its own physical laws. It's hard to know which of these, if any, describes our universe. The other main contender is called loop quantum gravity LQG. LQG is a more conservative approach. It doesn't require extra dimensions or new particles. Instead, it takes the principles of quantum mechanics and applies them directly to the fabric of spacetime as described by general relativity. In LQG, spacetime itself is not smooth and continuous. It is quantized. It's made of discrete, indivisible chunks or atoms of spacetime on the order of the Planck length. You can think of it like a piece of cloth. From a distance, it looks smooth, but up close, you can see the individual threads. According to LQG, space is a network of interconnected loops, and this network evolving in time is what we call spacetime. One of the striking predictions of LQG is that it might eliminate the singularity at the Big Bang. In this theory, the universe didn't begin from an infinitely dense point. Instead, it bounced from a previous contracting universe. This is the big bounce model. The next big discovery will be the first piece of experimental evidence that favors one of these theories over the other, or points to a completely new idea. This evidence is very hard to come by. One potential avenue is cosmology. Theories like LQG and some versions of string theory make specific predictions about the very early universe that might have left an imprint on the cosmic microwave background or the distribution of galaxies. For example, if the Big Bounce model is correct, it might have produced specific types of gravitational waves that we could one day detect. Another idea is to look for tiny violations of fundamental symmetries. Some theories of quantum gravity predict that the speed of light might not be exactly constant for all energies. High-energy gamma-ray photons from distant cosmic events might travel slightly slower or faster than low-energy photons. And telescopes like the Cherenkov telescope array could look for this tiny time delay. Finding such a signal would be revolutionary. It would be the first experimental hint of the quantum nature of space-time, and a major step towards a final unified theory of reality. For number 13, we will detect the oldest light in the universe. We have seen the afterglow of the Big Bang. The cosmic microwave background CMB is the oldest light we can see. It was released about 380,000 years after the Big Bang, when the universe became transparent. But what happened before that? The first 380,000 years are opaque to us because the universe was a dense, hot plasma that was impenetrable to light. To look back further, we need a different kind of messenger, one that could travel freely through this early plasma. That messenger is the neutrino. Neutrinos are tiny, almost massless elementary particles. They are sometimes called ghost particles because they interact so weakly with other matter. Trillions of neutrinos from the sun are streaming through your body every second, and you don't feel a thing. This weakness is also their strength. Because they barely interact with anything, they could travel unimpeded through the dense, early universe. In the first second after the Big Bang, the universe was a hot soup of particles, including a huge number of neutrinos. As the universe expanded and cooled, these neutrinos decoupled from the rest of the matter and began to stream freely through space. This happened when the universe was just 1 second old. These primordial neutrinos should still be all around us today, forming a cosmic neutrino background CMB, a faint echo of the universe's first second, just as the CMB is an echo of its 380th year. The problem is that these neutrinos are incredibly difficult to detect. As the universe has expanded, their energy has dropped to extremely low levels, much lower than the neutrinos produced by the sun or other astrophysical sources. They are moving very slowly now. Detecting them directly is currently beyond our technological capabilities. The proposed Ptolemy experiment at Princeton University is designed to try. The idea is to use a large target of tritium, a radioactive isotope of hydrogen. When tritium decays, it emits an electron and a neutrino. If one of the relic neutrinos from the Big Bang hits a tritium nucleus at just the right moment, it can give the emitted electron a tiny extra kick of energy. By measuring the energies of the electrons from tritium decay with extreme precision, Ptolemy hopes to find a small excess of electrons at the very highest energies, which would be the signature of the cosmic neutrino background. It is an incredibly challenging experiment. Even if we can't detect the CMB directly, we can see its effects. These relic neutrinos have a small but measurable impact on the cosmic microwave background and the large-scale structure of galaxies. They carry energy and contribute to the expansion rate of the early universe. By making very precise measurements of the CMB with experiments like the Simons Observatory, we can infer the properties of the CMB. We have already used this method to confirm that there are 3 types of neutrinos, as the Standard Model predicts. The next big discovery will be the first direct detection of the CMB by an experiment like Ptolemy, or a measurement from cosmology that is so precise it can tell us the mass of the neutrinos and look for any new exotic physics in the neutrino sector. Detecting the cosmic neutrino background would open a brand new window onto the universe. It would be our earliest possible glimpse of the cosmos, a snapshot of what the universe was like when it was just 1 second old. Chapter number 12, we will solve the mystery of matter's dominance. According to our best theories of physics, the Big Bang should have created equal amounts of matter and antimatter. For every particle, like a proton, there should have been an antiparticle and antiproton with the same mass but opposite charge. When a particle and its antiparticle meet, they annihilate each other in a flash of energy. So, in the early universe, there should have been a furious storm of creation and annihilation. As the universe expanded and cooled, all the matter and antimatter should have found each other and annihilated, leaving behind a universe filled with nothing but light. But that's not what we see. We live in a universe made almost entirely of matter. The galaxies, the stars, the planets, and us, we are all made of matter. There is very little antimatter to be found. For some reason, there was a tiny imbalance in the early universe. For every billion antiparticles, there were 1,000,000,001 particles. All the pairs annihilated, and the tiny leftover fraction of matter is what makes up everything we see today. This is the baryon asymmetry problem. Why was there an imbalance? In 1967, the Soviet physicist Andrei Sakharov laid out 3 conditions that must be met for a universe to evolve from a state of perfect matter-antimatter symmetry to a state dominated by matter. First, there must be a process that violates baryon number conservation. Baryon number is a quantum number that is cloned for baryons like protons and neutrons and 1 for antibaryons. This condition means there must be a way to create more baryons than antibaryons. The standard model of particle physics does allow for this, but the effect is far too small to explain the observed asymmetry. Second, there must be a violation of C-symmetry and CP-symmetry. C-symmetry means the laws of physics should be the same if you swap a particle with its antiparticle. CP-symmetry means the laws should be the same if you swap a particle with its antiparticle and also view its mirror image. We know from experiments with particles called kaons and B mesons that CP symmetry is violated in nature, but again, the amount of violation we've measured in the standard model is not nearly enough to account for the dominance of matter. Third, these processes must have happened out of thermal equilibrium. In a state of perfect thermal equilibrium, any process that creates an excess of baryons would be balanced by a reverse process that destroys it. The rapid expansion of the early universe provides this necessary departure from equilibrium. So, the standard model contains all the necessary ingredients, but the quantities are all wrong. This is a strong indication that there must be new physics beyond the standard model. We need a new source of CP violation. One place to look for it is in the behavior of neutrinos. The T2K Tokai to Kamioka experiment in Japan is studying neutrino oscillations, the process where neutrinos change from one type or flavor to another as they travel. They create a beam of muon neutrinos at J-Park on the east coast of Japan and fire it 295 kilometers through the Earth to the Super Kamiokande detector in the mountains of western Japan. They measure how many of the muon neutrinos have turned into electron neutrinos. Then they do the same experiment with antineutrinos. If CP symmetry were perfect, the rate of oscillation should be the same for both. But in 2020, the T2K experiment reported strong evidence that neutrinos and antineutrinos oscillate at different rates. This is a new source of CP violation. It is still not clear if this effect is large enough to explain the matter-antimatter asymmetry, but it is a very promising lead. On future experiments like Dune Deep Underground Neutrino Experiment in the US and Hyperkamiokande in Japan will measure this effect with much greater precision. Another possibility is that the asymmetry was generated by the decay of new heavy particles that existed in the very early universe, as predicted by grand unified theories or models involving supersymmetry. These particles would have decayed in a way that violated CP symmetry, producing slightly more matter than antimatter. The LHC is searching for such particles. The next big discovery will be the confirmation of a large CP violating effect in the neutrino sector, or the discovery of a new particle at the LHC that fits the bill. Solving the baryon asymmetry problem is fundamental to understanding our own existence. It's about answering the question, why is there something rather than nothing? Number 11, the cosmic axis of evil will be explained. The cosmic microwave background CMB is remarkably uniform. The temperature is the same in all directions to 1 part in 100,000. But when scientists looked at the high precision maps of the CMB from the WAP and Planck satellites, they found a few strange, large-scale anomalies that don't seem to fit the standard model of cosmology. The most famous and perplexing of these is the axis of evil. This refers to an unexpected alignment of the largest patterns, the hot and cold spots, in the CMB. The standard cosmological model, which includes inflation, predicts that the temperature fluctuations on the CMB should be random. There should be no preferred direction in the universe. But that's not what we see. The largest scale patterns, the so-called quadrupole and octupole, seem to be aligned with each other. And even more strangely, this axis of alignment seems to point directly at our solar system's ecliptic plane, the plane in which the planets orbit the sun. This alignment is highly unlikely to be a coincidence. The odds of it happening by chance are estimated to be less than 1 in 10,000. It's called the axis of evil because it threatens to undermine our most fundamental assumption about the universe, the cosmological principle. This principle states that on large scales, the universe is homogeneous and isotropic, meaning it looks the same everywhere and in every direction. This principle is the bedrock of modern cosmology. If there is a preferred direction in the universe, then our whole model of the cosmos could be wrong. So what could be causing it? There are 3 main possibilities. The first is that it's a fluke. It's a 1 in 1,000 chance, but rare things happen. Maybe we just happen to live in a universe where the CMB fluctuations lined up this way by pure coincidence. As we collect more data, we can test this, but it's a hard hypothesis to disprove. The second possibility is that the signal is not cosmological at all. It could be some subtle, unaccounted for foreground contamination from our own solar system or galaxy that is creating the illusion of an alignment. Scientists on the Planck team have spent years searching for such an error, looking at things like microwave emissions from dust in the solar system, but they haven't been able to find anything that can explain the signal. The third and most exciting possibility is that the axis of evil is real and is telling us something new and profound about the universe. Perhaps the universe is not perfectly isotropic. Maybe the overall geometry of the universe is not flat, but slightly anisotropic, like a donut or some other complex topology. This could create a preferred direction. Or maybe it's a remnant of some exotic physics in the very early universe before or during inflation. Perhaps the field that drove inflation was not a simple scalar field, but something more complex that left behind a directional imprint on the cosmos. Some even more speculative theories suggest it could be a sign of physics from before the Big Bang, a remnant of a previous cosmic cycle. The next big discovery will be to figure out which of these possibilities is correct. Future CMB polarization experiments, which measure the orientation of the CMB light waves, could provide crucial new information. If the anomaly is also seen in the polarization data in a specific way, it would be much harder to explain as a foreground effect or a statistical fluke. It would strengthen the case for new physics. If we can confirm that the axis of evil is a real cosmological feature, it would force a revolution in our understanding of the universe. It would mean that the simple, elegant picture of a perfectly isotropic universe that has guided us for a century is wrong. It would mean the cosmos has a secret structure, a preferred direction written across the entire sky. Number 10, we may find we live in a universe that bounces. The standard Big Bang model tells us the universe began from a singularity, an infinitely hot, infinitely dense point. But this singularity is a problem. It's a point where the laws of physics as we know them break down. It's a mathematical infinity that tells us our theory, general relativity, is incomplete. For many physicists, the idea of a beginning of time itself is philosophically unsatisfying. What came before the Big Bang? The Standard Model has no answer. This has led some to explore an alternative idea, a cyclic universe. The idea is that our universe is just one in an endless series of cycles of expansion and contraction. The Big Bang wasn't a beginning, but a big bounce, a transition from a previous contracting universe. The idea of a bouncing universe is not new. It has been around for decades, but it has gained new life with the development of theories like loop quantum gravity. As we've seen in LQG, spacetime is quantized. This quantization puts a limit on how much matter and energy can be squeezed into a given volume. It gets rid of the singularity. As a universe contracts, it reaches a point of maximum density, the Planck density, and then the quantum properties of space-time itself create a powerful repulsive force that causes it to bounce and begin expanding again. In this picture, our universe emerged from the collapsed state of a previous one. Another class of cyclic models comes from string theory and M theory, particularly the ekpyrotic model proposed by Paul Steinhardt and Neil Turok. In this model, our universe is a 3D brain existing in a higher dimensional space. There is another parallel brain. The universe goes through long periods of slow expansion and cooling. Then the two brains are pulled together and collide. This collision releases a tremendous amount of energy, which heats up our brain and triggers a period of expansion that we perceive as the Big Bang. The brains then separate, and the cycle begins again. This model avoids a singularity and also offers an alternative to inflation for explaining the universe's flatness and uniformity. How could we ever test such a mind-bending idea? Both the Big Bounce and the ekpyrotic models make specific, testable predictions. One of the most important relates to primordial gravitational waves. Standard inflation predicts a background of gravitational waves with a wide range of wavelengths, including very long ones. The detection of these long wavelength gravitational waves via their B-mode polarization signature in the CMB would be strong evidence for inflation. Most cyclic models, on the other hand, do not produce a significant background of primordial gravitational waves. The bang in these models is much less violent than in inflation, so if our next generation of CMB experiments fail to find any B-mode signal from primordial gravitational waves, it would be a major blow to inflation and would lend support to cyclic models. Cyclic models also might produce a different spectrum of primordial density fluctuations, the seeds of galaxies, which could be detected with future high-precision galaxy surveys. The next big discovery could be the definitive non-detection of primordial gravitational waves from inflation. If, after years of searching with incredibly sensitive experiments like CMB-S4, we find nothing, it will force cosmologists to take bouncing and cyclic models much more seriously. It would represent a paradigm shift in our understanding of cosmic origins. It would mean that our universe did not have a beginning, and it will not have a final end. It is part of an eternal, magnificent cycle of death and rebirth. Number 9. We will find a crack in Einstein's theory of gravity. Or Albert Einstein's theory of general relativity, published in 1915, is one of the most successful scientific theories of all time. It describes gravity as the curvature of space-time caused by mass and energy. Its predictions have been confirmed by every experiment we have ever thrown at it. It correctly predicted the bending of starlight by the sun, the precise orbit of Mercury, the existence of black holes, and the ripples in space-time known as gravitational waves. It is the foundation of our modern understanding of the cosmos, but we know it can't be the final word. It's a classical theory, and it breaks down at the quantum level, inside black holes, and at the Big Bang. And the discoveries of dark matter and dark energy, which together make up 95% of the universe might also be hinting that general relativity is incomplete on cosmological scales. So far, we have explained these phenomena by inventing new invisible substances, dark matter, and dark energy. But what if we're wrong? What if the reason galaxies spin too fast and the universe's expansion is accelerating is not because of some mysterious stuff, but because our theory of gravity is wrong on these large scales? This is the idea behind modified gravity theories. The most famous of these is called modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram in the 1980s. MOND suggests that Newton's law of gravity, and by extension Einstein's, is correct in high acceleration environments like our solar system, where gravity is strong. But in very low acceleration environments like the outer edges of galaxies, gravity behaves differently. It becomes stronger than predicted. This stronger gravity would explain the fast rotation of galaxies without the need for dark matter. MOND has had some remarkable successes in predicting the rotation curves of galaxies, often better than dark matter models, but it has struggled to explain the behavior of galaxy clusters and the patterns we see in the cosmic microwave background. There are many other modified gravity theories. Some are extensions of general relativity, adding new fields or terms to Einstein's equations. These theories often try to explain the accelerating expansion of the universe without dark energy. They propose that gravity itself becomes repulsive on very large scales, pushing the universe apart. These theories are often very complex, and it is difficult to make them consistent with all the observational data we have, particularly from both cosmology and the solar system. The next big discovery will be the first piece of evidence that shows a clear deviation from general relativity. We are entering an era of high-precision cosmology where we can test gravity in new ways. The Euclid Space Telescope and the Vera C. Rubin Observatory will map the distribution of millions of galaxies. By studying how light from these galaxies is bent by the gravity of intervening matter, a technique called weak gravitational lensing, and how galaxies cluster together, they can map the growth of structure in the universe over time. General relativity makes very specific predictions about how this structure should grow. If we find that galaxies are clustering in a way that is different from the predictions of general relativity, it would be a smoking gun for modified gravity. Another avenue is gravitational waves. By comparing the arrival time of gravitational waves and light from the same event, like a neutron-star merger, we can test if gravity travels at the speed of light, a key prediction of general relativity. So far it does, but future, more sensitive detectors might find a tiny difference. Finding any crack in Einstein's theory would be a monumental event. It would open the door to a new, deeper understanding of gravity, the most fundamental and mysterious force in the universe. Number 8. A fifth force of nature will be uncovered. The Standard Model of Particle Physics describes 4 fundamental forces: the strong nuclear force, which holds atomic nuclei together; the weak nuclear force, which is responsible for radioactive decay electromagnetism, which governs light and magnetism and gravity. For decades, this picture has been complete, but there are hints that there might be a fifth force, a new interaction that we haven't accounted for. One of the most persistent hints comes from the behavior of a particle called the muon. The muon is like a heavy cousin of the electron, about 200 times more massive. Like the electron, it has a property called spin, which makes it behave like a tiny magnet. When you put a muon in a powerful magnetic field, its spin wobbles or precesses like a spinning top. The rate of this wobble can be predicted with incredible precision by the Standard Model. The prediction includes all the known forces and particles, which contribute to the wobble through a sea of virtual particles that constantly pop in and out of existence around the muon. The muon G2 experiment at Fermilab is designed to measure this wobble with exquisite accuracy. In 2021, they announced their first results. They found that the muons were wobbling slightly faster than the Standard Model predicted. The result was not yet statistically significant enough to claim a discovery, but it confirmed a similar anomaly seen in an earlier experiment at Brookhaven National Laboratory. In 2023, they released a new, more precise result that strengthened the evidence for a deviation. If this anomaly holds up, it would be a clear sign of new physics. The most straightforward explanation is that there is a new force of nature carried by a new particle that is interacting with the muon and giving its spin an extra little push. This would be the first discovery of a fundamental particle or force since the Higgs boson in 2012. Another hint comes from experiments at the LHC. The LHCb experiment, which studies the decays of particles containing bottom quarks, has seen some strange anomalies. They have found that certain types of B mesons seem to decay into muons slightly less often than they decay into electrons. According to the standard model, this should not happen. The weak force should treat electrons and muons identically, a principle called lepton universality. This violation suggests that there could be a new force that interacts differently with muons and electrons. What could this fifth force be like? It's likely to be very weak or act only over very short ranges, which is why we haven't seen it before. It could be a force that primarily interacts with dark matter and only very weakly with normal matter, providing a portal between the visible and dark sectors of the universe. Some theories suggest a new force could be related to the Higgs boson, or it could be a new long-range force carried by a very light particle. And experiments are underway to search for such a force directly, often by looking for tiny, unexplained forces between objects in a laboratory. The discovery of a fifth force would completely revolutionize particle physics. It would shatter the neat picture of the standard model and open up a whole new landscape of particles and interactions to explore. It would show that our understanding of the fundamental building blocks of the universe is still very much a work in progress. Number 7, the cosmic cold spot, will give up its secret. On the maps of the cosmic microwave background, there is a particularly large and unusually cold patch of the sky. It's called the CMB cold spot. It was first discovered by the WMAP satellite in 2004 and later confirmed by the Planck satellite. It's about 70 microkelvins colder than the average CMB temperature of 2.725 Kelvin. While there are hot and cold spots all over the CMB map, this one is a major outlier. The chance of such a large and cold spot appearing in the standard cosmological model due to random quantum fluctuations is only about 1 in 50. This has led many to speculate that it might not be a random fluctuation at all, but a sign of something else. One of the leading explanations is that the cold spot is caused by a supervoid, an enormous region of space that is unusually empty of galaxies. According to the integrated Sachs-Wolf effect, photons from the CMB gain a little bit of energy as they fall into the gravitational well of a large structure like a supercluster of galaxies, and then they lose that energy as they climb back out. If the universe's expansion is accelerating due to dark energy, then by the time the photons climb out, the supercluster has expanded and its gravitational well is shallower. So the photons don't lose as much energy as they gained. The net effect is that they come out slightly hotter, creating a hot spot on the CMB. Conversely, if the photons pass through a giant void, they lose energy as they enter it and don't gain it all back on the way out because the void is stretching while they are inside. This would create a cold spot on the CMB. Astronomers have looked for a supervoid in the direction of the cold spot. They have found a large underdense region, but it doesn't seem to be large or empty enough to explain the entire temperature drop. The debate is ongoing about whether the void is sufficient. A far more exotic and speculative explanation is that the cold spot is a bruise on our universe, the result of a collision with another universe. This idea comes from the eternal inflation and string theory landscape picture of the multiverse. In this scenario, our universe is just one bubble in a vast, eternally inflating multiverse. Other bubble universes are constantly being created. It is possible that in the distant past, another bubble universe collided with ours. The collision would have been a cataclysmic event that could have left a permanent scar on our cosmos, a circular patch on the CMB with a slightly different temperature. The cold spot has some features that are consistent with this model, but the evidence is far from conclusive. The next big discovery will be a definitive explanation for the cold spot. Future, more detailed galaxy surveys, like the one that will be conducted by the Euclid telescope, will be able to map the 3D structure of the universe in the direction of the cold spot with much greater precision. This will allow us to determine for sure if there is a supervoid there and if it is large enough to explain the effect. If it turns out that there is no supervoid or it is too small, then the case for a more exotic explanation like a multiverse collision becomes much stronger. Another way to test this is by looking at the polarization of the light from the cold spot. A multiverse collision might leave a specific signature in the polarization pattern that would be different from a random fluctuation or a supervoid. Uncovering the true nature of the cold spot would either confirm our standard cosmological model's statistical predictions or provide the first tantalizing piece of evidence that our universe is not alone. Number 6. We will detect life beyond Earth. For all of human history, we have looked up at the stars and wondered, are we alone? So far, the answer has been silence, but we are now, for the first time, developing the technology to search for life on other worlds in a systematic way. The search is proceeding on two main fronts: the search for biosignatures within our own solar system, and the search for biosignatures and technosignatures on exoplanets orbiting other stars. Within our solar system, the most promising places to look for life are Mars and the icy moons of Jupiter and Saturn, such as Europa and Enceladus. Mars once had liquid water on its surface, and it may still exist underground. Rovers like Perseverance are searching for signs of past microbial life in ancient river deltas. Future missions could drill deep beneath the surface, where life might still cling on, protected from the harsh surface radiation. Europa and Enceladus are even more tantalizing. They are covered in a thick shell of ice, but beneath it, they are thought to have vast global oceans of liquid water warmed by tidal forces from their parent planets. We have seen plumes of water vapor erupting from cracks in the ice of Enceladus, which means we could potentially fly a spacecraft through these plumes and sample the ocean's contents for organic molecules or even microbial life without ever having to land and drill. The search for life on exoplanets is a much grander challenge. We have now discovered over 5,000 exoplanets. Some of these are small rocky planets orbiting in the habitable zone of their star, the region where temperatures are right for liquid water to exist on the surface. The James Webb Space Telescope is a powerful tool for this search. When an exoplanet passes in front of its star, a tiny fraction of the starlight passes through the planet's atmosphere. JWs can analyze the spectrum of this light to look for the chemical fingerprints of gases in the atmosphere. The presence of gases like oxygen, methane, and water vapor, especially in combination, could be a strong biosignature, a sign of life. For example, on Earth, oxygen is overwhelmingly produced by photosynthesis. Finding a lot of oxygen in an exoplanet's atmosphere would be a very exciting discovery. The other approach is the search for extraterrestrial intelligence, or SETI. This is the search for technosignatures, signs of advanced technology. This has traditionally involved using radio telescopes to listen for artificial signals from other star systems. So far, we have found nothing conclusive, but the search is expanding. We are also looking for other signs of technology, like powerful laser signals used for communication or propulsion, or even giant artificial structures like Dyson spheres built around stars to capture their energy. The Vera C. Rubin Observatory, with its ability to scan the entire sky every few nights, will be a powerful tool for finding unusual or artificial-looking objects. The next big discovery could be the detection of a convincing biosignature in the atmosphere of a nearby exoplanet by JWST. It might be a combination of gases that is very difficult to explain through purely geological or chemical processes. Or it could be the conformation of complex organic molecules in the plumes of Enceladus. Or, perhaps most profoundly, it could be the detection of a clear, unambiguous artificial signal by a SETI project. Any of these discoveries would be one of the most significant moments in human history. It would fundamentally change our place in the universe. It would mean that the transition from non-life to life is not a unique fluke that happened only on our planet, but a common outcome of the laws of chemistry and physics. It would mean the universe is teeming with life, and we are just one small part of a vast cosmic biology. Number 5, the universe's ultimate destiny will be revealed. The fate of the universe is tied to the nature of dark energy. If dark energy is the cosmological constant, the energy of empty space, then its density will remain constant as the universe expands. In this scenario, the universe will continue to expand forever at an accelerating rate. This leads to a future known as the Big Freeze or heat death. As the universe expands, galaxies will move away from each other faster and faster. Eventually, they will cross a cosmic horizon and disappear from our view. The sky will become dark and empty. The stars within our own local group of galaxies will eventually burn out. The remaining matter will be locked up in black holes and dead stars. Over immense, unimaginable timescales, even the black holes will evaporate through Hawking radiation. The universe will end up as a cold, dark, empty void, filled with a dilute gas of photons and elementary particles, approaching a state of maximum entropy where nothing interesting can ever happen again. But what if dark energy is not a constant? What if it is a dynamic field like quintessence? In that case, the future is much less certain. If the strength of dark energy decreases over time or even becomes attractive, gravity could eventually win. The expansion of the universe could slow down, stop, and reverse. This would lead to a big crunch. The universe would begin to contract, with galaxies rushing towards each other. The temperature and density would rise until everything is crushed back into a single, hot, dense singularity, perhaps triggering a new Big Bang in a cyclic universe scenario. There is a third, more violent possibility. If the strength of dark energy increases over time, a scenario known as phantom energy, it could lead to a big rip. In this future, the accelerating expansion becomes so powerful that it overwhelms all other forces. First, it would tear apart clusters of galaxies. Then, it would overcome the gravity holding individual galaxies together. A few million years before the end, it would rip apart our solar system. In the final moments, it would be strong enough to overcome the electromagnetic and nuclear forces, tearing apart planets, stars, and even atoms and their nuclei. The fabric of space-time itself would be torn asunder. The next big discovery will be to determine which of these fates awaits us. Our next generation of cosmological surveys, like Euclid and the Roman Space Telescope, are designed to measure the properties of dark energy with high precision. They will do this by mapping the distribution of galaxies and supernovae across cosmic time. This will allow them to measure the equation of state of dark energy, a parameter known as dew. If dark energy is the cosmological constant, WOP will be exactly 1. If WOP is greater than 1, it points to a quintessence-like field, and a big crunch might be possible. If W is less than 1, it means we are dealing with phantom energy, and the big rip is our destiny. Our current measurements show that W is very close to 1, but there is still enough uncertainty to allow for these other possibilities. By narrowing down the value of W, these future telescopes will be able to look into the cosmic crystal ball and tell us how the story of our universe will end. Number 4, we will directly observe a white hole. And general relativity is a time-symmetric theory. This means that any solution to Einstein's equations has a time-reversed version that is also a valid solution. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. It is a one-way membrane. The time-reversed solution of a black hole is a white hole. A white hole is a hypothetical region of space-time where nothing can enter from the outside and matter and light can only escape. It is a place from which things are spewed out, but to which nothing can return. It's like a cosmic fountain. If you were watching a movie of matter falling into a black hole and then played the movie in reverse, you would see a white hole. For a long time, white holes were considered a mathematical curiosity with no physical relevance. The process that forms a black hole, the collapse of a massive star, is a one-way process. There is no known physical process that could form a white hole. They would have to have been created in the Big Bang itself. Furthermore, they are thought to be extremely unstable. If even a single photon of light were to fall towards a white hole, it would be infinitely blue-shifted as it approached the event horizon and would gain enough energy to collapse the white hole into a black hole. But recently, some physicists have begun to take the idea of white holes more seriously, particularly in the context of quantum gravity and the black hole information paradox. And one idea proposed by Carlo Rovelli and others in the framework of loop quantum gravity is that black holes might not live forever. When a black hole evaporates via Hawking radiation, it shrinks. As it approaches the Planck scale, the quantum properties of space-time could prevent it from collapsing into a singularity. Instead, the collapsing matter could bounce and emerge as a white hole. In this picture, a white hole is the end stage of a black hole's life. Information that falls into the black hole is not destroyed, but is stored and eventually released when it emerges from the white hole. This would be a very long process. A solar mass black hole would take an immense amount of time to evaporate, but for primordial black holes formed in the early universe, this could have already happened. So, how could we ever see one? If a primordial black hole formed in the early universe and has now bounced to become a white hole, its death would be an explosive event, releasing a burst of high-energy particles and radiation. Some have suggested that a certain class of mysterious, fast radio bursts, FRBs, or short, high-energy gamma-ray bursts, could be the signature of a dying primordial black hole turning into a white hole. These signals would have a specific energy and wavelength that could distinguish them from other astrophysical phenomena. Another idea is that dark matter itself could be composed of tiny, Planck-sized remnants of evaporated black holes. The next big discovery would be the detection of a signal that can only be explained by a white hole. This would most likely be a specific type of high-energy transient event detected by our radio or gamma-ray telescopes that matches the predictions of a black hole bounce. For example, a signal at a specific radio frequency, around 10 raised to the power of 14 hertz, has been predicted as a potential signature. Finding such an event would be a stunning confirmation of quantum gravity theories like LQG. It would solve the information paradox and would completely change our understanding of the life cycle of black holes. It would mean that the one-way doors of the universe might not be one-way after all. Number 3. A wormhole will be discovered. A wormhole, or an Einstein-Rosen bridge, is a speculative structure in space-time that could act as a shortcut through space and time. It is a solution to the equations of general relativity, just like a black hole. In essence, it connects two different points in space-time. You could enter a wormhole in our galaxy and emerge in the Andromeda galaxy moments later, or even in the past or future. The idea has been a staple of science fiction for decades, but could they be real? The simplest type of wormhole described by general relativity is not traversable. If you tried to fly into one, the throat of the wormhole would collapse so quickly that not even a beam of light would have time to get through. It would pinch off and form a singularity, crushing you. To keep a wormhole open and make it traversable, you would need to prop it up with some kind of exotic matter. This is matter that has a negative energy density, or in other words, matter with anti-gravity. It would push the walls of the wormhole apart, holding it open. We have never observed any matter with these properties. The closest thing we know of is the Casimir effect in quantum mechanics, where a small amount of negative energy density can be created between two closely spaced metal plates, but it's not clear if you could collect enough of this to stabilize a wormhole. However, recent developments in theoretical physics have connected the idea of wormholes to the strange phenomenon of quantum entanglement. Entanglement is what Einstein called spooky action at a distance. It's a connection between two quantum particles where measuring a property of one particle instantly influences the property of the other, no matter how far apart they are. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a radical idea they called ER equals EPR. ER stands for Einstein-Rosen-Bridges wormholes, and EPR stands for Einstein-Podolsky-Rosen, the authors of the paper that first described entanglement. Their conjecture suggests that entanglement and wormholes are two different descriptions of the same thing. Whenever two particles are entangled, they are connected by a microscopic, non-traversable wormhole. This is a profound idea that connects the geometry of space-time general relativity with the weirdness of quantum mechanics. It has led to new insights into the black hole information paradox. It suggests that the inside of a black hole might be connected to the Hawking radiation it emits via a network of wormholes. This could be the mechanism by which information escapes. While these quantum wormholes would be microscopic and not something you could fly a spaceship through, the idea that the universe is threaded with these connections is a major theoretical leap. Could a traversable wormhole exist? It is still highly speculative. Some theories of modified gravity or quantum gravity might allow for their existence without exotic matter. If they do exist, how could we find one? A wormhole would have strong gravitational effects. It would bend light, just like a black hole. We could potentially detect one by looking for specific gravitational lensing signatures. If a wormhole passed in front of a distant star, it might create a unique brightening pattern that is different from a normal star or a black hole. Another idea is that the mouth of a wormhole might radiate energy in a specific way. If a wormhole connected two different regions of the universe, gas and stars could fall into it from the other side and emerge from our side, creating a visible object that doesn't seem to have a local source of matter. The next big discovery would be the detection of a gravitational lensing event, or an astronomical object that cannot be explained by anything else. It would be a long shot, but if we found one, it would mean that the universe has a hidden topology, a secret set of tunnels that could one day allow for travel across cosmic distances. Number 2, we will directly image an Earth-like exoplanet. We have found thousands of exoplanets, but we have never really seen one. Almost all of them have been detected indirectly by methods like the transit method, looking for the tiny dip in a star's light as a planet passes in front of it, or the radial velocity method, looking for the slight wobble of a star caused by the gravitational tug of an orbiting planet. We have managed to take a few direct images of exoplanets, but these have all been of giant Jupiter-sized planets orbiting very far from their stars. These planets are large, young, and still glowing with the heat of their formation, which makes them bright in infrared light. Taking a picture of a small, rocky, temperate planet like Earth is a vastly greater challenge. The problem is one of contrast and distance. An Earth-like planet is incredibly faint compared to its star. The sun is about 10 billion times brighter than the Earth in visible light. Trying to see an Earth-like planet next to its star is like trying to spot a firefly next to a searchlight from thousands of miles away. The star's glare completely overwhelms the planet's feeble, reflected light. To directly image such a planet, you need a telescope that can do two things: achieve incredibly high resolution to separate the planet from the star, and have a way to block out the starlight to reveal the faint planet next to it. This will require a new generation of extremely large ground-based telescopes and advanced space telescopes. On-the-ground telescopes like the extremely large telescope ELT, the 30-meter telescope TMT, and the Giant Magellan Telescope GMT are currently under construction. These telescopes will have primary mirrors that are 30 to 40 meters in diameter, far larger than any existing telescope. They will be equipped with advanced adaptive optics systems to correct for the blurring effect of Earth's atmosphere, and sophisticated coronagraphs, instruments that act like an artificial eclipse to block the starlight. These telescopes might be able to take the first blurry point of light images of the nearest potentially habitable exoplanets, like those orbiting Proxima Centauri or in the TRAPPIST-1 system. But to get a truly clear picture, we will likely need to go to space. NASA is studying concepts for a future flagship space telescope designed specifically for this purpose. One concept is the Habitable Worlds Observatory HWO. This would be a large space telescope with a mirror, perhaps 6 meters in diameter or larger, operating in the visible and ultraviolet parts of the spectrum. It would be equipped with the most advanced coronagraph technology ever developed. Its primary goal would be to survey dozens of nearby sun-like stars and directly image any Earth-like planets orbiting them. The next big discovery will be the first resolved image of a pale blue dot orbiting another star. It might not be a detailed picture showing continents and oceans. At first, it will likely be just a single pixel of light. But from that one pixel, we can learn a huge amount. By measuring the color of the light, we could tell if the planet has an atmosphere, and maybe even if it has clouds or oceans. By observing the planet over time as it rotates, we could see the brightness change, allowing us to map its surface features in a crude way. We could look for the red edge of vegetation, or the glint of sunlight off a liquid surface. And most importantly, we could use a spectrometer to analyze the light from that pixel and search for biosignatures like oxygen and methane. This discovery would be more than just a scientific achievement. It would be a deeply profound culture-shifting moment. For the first time, we would see another Earth, another potential home for life, and we would know with certainty that our world is not unique. Number 1, the first evidence of the multiverse will be found. The idea that our universe is not the only one, that we are part of a vast collection of universes called the multiverse, has moved from the realm of philosophy and science fiction to a serious, though controversial, topic in modern cosmology. The idea arises naturally from some of our most promising physical theories. One version of the multiverse comes from the theory of eternal inflation. In this picture, the super fast expansion of the early universe, inflation, didn't happen just once. It is happening all the time. In some parts of the wider cosmos, our universe is just one bubble that nucleated out of this eternally inflating space, a region where inflation stopped. But beyond our observable horizon, inflation continues, constantly spawning new bubble universes. Each of these bubbles could have different physical constants, different particles, and even different numbers of dimensions. Most would be sterile and inhospitable to life. But in a small fraction of them, the conditions would be just right for stars, galaxies, and life to form. This provides a potential explanation for why the physical constants in our universe seem so finely tuned for our existence. Another version of the multiverse comes from the many worlds interpretation of quantum mechanics as proposed by Hugh Everett. As we discussed, this theory suggests that the universe splits into multiple copies every time a quantum measurement is made. This creates a branching tree of parallel universes where every possible outcome of every event is realized in some branch. This is a very different kind of multiverse where the other universes are not physically separate bubbles, but parallel realities coexisting with our own. A third version comes from string theory's landscape, which suggests a huge number of possible solutions to the theory's equations, each corresponding to a universe with different laws of physics. But is any of this science? If these other universes are fundamentally unobservable, then the multiverse is not a testable scientific theory. So the key question is, could we ever find evidence for it? It is incredibly difficult, but perhaps not impossible. If the eternal inflation picture is correct, it is possible that our bubble universe collided with another one in the distant past. As we saw with the CMB cold spot, such a collision could have left a bruise on our cosmic microwave background, a detectable circular pattern of temperature or polarization variations. The search for such a signature is ongoing in the Planck satellite data and will be a target for future CMB experiments. Another potential test relates to the fine-tuning problem. If we discover that the parameters of the standard model, like the mass of the Higgs boson, are not uniquely predicted by a final theory, but could have taken on other values, it would lend circumstantial support to the multiverse idea. It would suggest that we live in one of the rare universes where the values are right for us to be here to observe them. Some have even proposed more radical ways to test the many worlds interpretation. For example, some physicists argue that it might be possible, in principle, to build a quantum computer that could perform calculations in parallel universes and bring the results back, which would be a form of interaction with them. This is highly speculative, but it highlights that physicists are actively thinking about how to make the multiverse a testable hypothesis. The next big discovery will not be a definitive photograph of another universe. It will be subtle. It might be the discovery of a statistically significant circular anomaly in the CMB that cannot be explained by anything in our own universe. It could be a discovery at the LHC that shows our vacuum is not perfectly stable and could one day tunnel into another state, hinting at a larger landscape of possibilities. Or it could be a theoretical breakthrough in quantum gravity that forces us to accept the multiverse as a necessary consequence of the laws of nature. Finding the first piece of hard evidence for other universes would be the single greatest discovery in the history of science. It would dwarf the Copernican revolution. We would learn not only that we are not the center of the universe, but that our entire universe is just one tiny, insignificant part of a much grander and possibly infinite cosmic reality.